Here's another example of sketching a curve, and this is similar to the homework problem number 16 from 13.1 in the 9th edition. If you feel like you already know how to do these, you could fast forward the video to this next section. But I'm going to go ahead and work one more example because people tend to need one here. One thing that's worthwhile to notice from the start is because we know that cosine and sine go between -1 and 1, this tells me that x is between -1 and 1, since x is cosine. Y is between -1 and 1. And z is between -2 and √2. So our graph is only going to reside, again, front and back 1 unit, left and right 1 unit, and up and down square root of 2 units. So the curve is in here somewhere. Now we need to find a surface on which that curve lies. So we do that by eliminating parameters. Now if I took these two, I get x equals y. So that would tell me that my curve lies in the plane y equals x. Now as x and y bounce back and forth between -1 and 1 here, z is also bouncing back and forth, but I'm having a hard time kind of figuring out what that curve would look like in this blue plane. So then I might find another surface. So I might take y and z and eliminate the parameter. That would be y equals cosine of t and z equals √2 sine of t, which means that z over √2 equals sine of t. We've seen this kind of thing before. If we square both sides here and square both sides here and add them, we're going to get y squared plus z squared over 2 equals cosine squared plus sine squared, which is 1. So that surface right there is a cylinder. There's no x in it. So draw the circle, y squared, well, this is not a circle, this is an ellipse. Draw the ellipse, y squared plus z squared over 2, and then extend it in the x direction. That will be a surface that my curve is on. So I've drawn the green cylinder in our picture. So our curve that we're trying to draw is both on the green cylinder and on the blue circle. So we must have something going around here. Now I don't know which way it goes yet, but I want to get the idea that we have something that's going around like this. So think of taking this cylindrical surface and slicing it at an angle here, and that intersection is our curve. Now if we want to see which direction our curve goes, if t is 0, we'd be at 1, 1, 0. So at t equals 0, we're right here. Now I know it's moving that direction on the plane. So it's moving backwards and leftward from here. The question is it going up or is it going down? So what I want to do is look at what z is doing. If I look at z as a function of t, it's the sine curve. So at t equals 0, sine is 0, and then like so. So that means z starts at 0 and then it goes up to square root of 2. So it's starting going upwards. So I actually had the right direction there, but that was just a guess. So that's our curve. This one has actually something else interesting that you could do that we haven't seen. We eliminated the parameter here and got a surface, the blue plane. We eliminated the parameter here. We got the surface, this green cylinder. We could come up here and eliminate the parameter between these two. If you want to try that, I'll let you try that on your own, but you're going to end up getting a cylinder going this way. But this one has something different. We can actually eliminate the parameter with all three of them at once. If I take x squared and y squared and z squared, and add all three of those up, I'll get 2x squared plus y squared plus z squared equals 2 cosine squared plus 2 sine squared t. And if you factor out that 2, you'll be left with the cosine squared plus the sine squared is 1. And so what you have here, my picture's already kind of got a whole lot going on, but what you have here is a sphere of radius square root of 2. So I'm not going to try to draw this neatly because I've got so much going on in this picture already, but if I had this sphere of radius radical 2, that would be another surface on which that curve lies. Well, you wouldn't find all these surfaces, but for instance, if you had just found the sphere and the plane, you could think of this red sphere like an orange or something, and then we come along and cut it at an angle. And our curve is that edge. It's a lot going on in that one. Okay, a couple other things I want to take a look at. One is sometimes we need to parameterize a surface. So we have the equation of a surface, and we want to go backwards and find a curve on which that surface lies. And so here, we're looking for the intersection of these two surfaces. So we need to find parametric equations that, if I eliminate the parameter, will satisfy both this one and this one. You've parameterized curves before. It's similar to that, but it's a little bit more complicated because we have to satisfy both of these equations. Well, first of all, when I see this cylindrical, a cylinder here, then I'm going to go ahead and use the x equals cosine t sine t, y equals sine t, but 2 cosine t, because the radius is 2, and 2 sine t. If I eliminate the parameter, square this, I get 1. So that satisfies that one. And now we have to satisfy this one over here. Well, we've already parameterized x and y. So z equals x times y is just going to be to multiply these two. So that's going to be 4 sine t cosine t. So there's a couple problems like that in this section. We really aren't going to revisit this until the very end of the course. So it's your first introduction to this, but we're going to come back to it near the end of the course. One other topic in section 13.1, we've learned about these new kind of functions, vector-valued functions. And we talked about how to evaluate them and how to graph them. But what are some of the other things we often talk about functions? Things like domain, limit, continuity, derivatives. So that's what we're going to do. We're going to look at these new kind of functions and figure out how to do all the different calculus on them. So let's start with, let's suppose I have this vector-valued function. And you can also have one in 2 dimension, you just wouldn't have this third component. The domain for this function to be defined, each one of these have to be defined. So to find the domain, it's just the intersection of the domain of f, g, and h. So for example, if r of t is natural log of t, t squared, 1 over t minus 3, this one would lead to the domain of natural log. The argument has to be strictly positive. T squared, the domain is all real numbers. And this third component, the domain is all real values except for 3. So if we put that all together, we have to have positive numbers, but not 3. all positive numbers except 3. That would be the domain. So putting all that together, we would go from 0 to 3, not include 3, and then 3 from 3 to infinity. Okay, so domain is just the intersection of the domains. The limit, the way the limit is defined, is to take the limit of each of the component functions. And I'll let you look at your book for an example there. Continuity, the definition of continuity for a single variable function is just that that limit and the functional value have to be one and the same. And that's how we're going to define continuity here as well. If you need to go back and review that, how we define continuity or how we define limits, you could do that. So let's see, R of A. So as t approaches a, if I get the same thing as I would for that functional value, if that's the case, then we have continuity. R is continuous at a. Right? Your book has a little more information in there. I just kind of covered that lightly. In the next video, we'll take a look at derivatives.